Hi everyone. I hope you're all okay. I hope you've been able to get on with some of the practice work. I've not had anything handed in yet, which is a little disappointing. So what I thought to start with today is a walkthrough. So as many of you will not have done the paper, you know what? I believe in forgiveness, but do bear in mind we're only a few weeks away from your actual exams on this. You will have to take exams, so it is important that you get on with practicing. We're almost finished. We've just got the specific heat capacity and latent heat work with Mr. Welsh, who's working through that with you, I gather. But as far as the stuff that I'm teaching about gas laws, thermal expansion, that's all pretty much done now. So we really do need to concentrate on that practice. There's a lot of marks to gain very easily on the UFP exam, as you know, but you do need to practice. You do need to know how to answer the questions. I'm not going to take no for an answer on that. So what we're going to do is I'm going to switch to my best camera. There we go. Okay. And so we start off with question number 1, which is a good place to start, I think. A student investigates the behavior of a gas in a cylinder during an isochoric change. So it then says state the constant volume gas law. Isochoric means constant volume. I think one of my next video lessons with you is going to be to talk you through the different types of change, because I think you do need to know the names of them, and I might do a few other sort of little bits and pieces that I think are not strictly speaking part of the syllabus, but you know what, you could do with knowing it. So state the constant volume gas law. So the key idea is that for a fixed amount of gas, you ought to be able to do this in your sleep by now. At constant volume, the pressure is proportional to absolute temperature. You've got to say absolute temperature. It's not enough to just say temperature. Okay, so the next part is then to state 2 quantities which a student would have needed to keep the same throughout the experiment. This is actually an easy 2 marks because it's kind of up here. It's a fixed amount of gas, so it would be amount of gas, in other words, the number of moles of gas. And also says constant volume, so it would be the volume. Okay. So the next one we're going to look at now says the student obtains the results shown in table 1. So you've got pressure and temperature in degrees Celsius. You have to calculate the absolute temperature. So all we're going to do here is I'm just going to calculate the absolute temperature using a calculator. No harm in using a calculator. In fact, I always advise you to use it. So it's 356 plus 273 degrees Kelvin. Now, while on physics papers, you're given a lot of the physical constants in the inside of that front cover. This is one number that you will have to remember. Technically, it should be 273.14, but we tend to only go to 3 significant figures. So remember that 273 Kelvin is 0 degrees Celsius. So we add it to the temperature and we end up with 629. Next one is 261 plus 273, 534. 167 plus 273, 440. 135 plus 273 is 408. Next one's 41. I think no, 73. It's that easy. Now the question says calculate numbers in the tables, write the values in table 1, which I've just done. using the correct number of significant figures. Well, I've got 3 significant figures here. I've got 2 or 3. So 3 is what I need on there. And it then says suggest a suitable unit. Well, it's Kelvin. That's easy. So the next part of the question then says plot a graph of pressure on the y-axis versus T on the x-axis and explain whether or not this proves the constant volume gas law. So we have to be quite careful here. So what we have to do is use our graph. Now it's told me to put pressure on the y-axis and temperature on the x-axis. So pressure goes on the y-axis, temperature on the x-axis. So if I look at my values, now it would make no sense to start at 0 here because my lowest value of pressure is just under half of what my highest value is. So half of my graph paper wouldn't be very well used. So I need to start below 100 and go up to 200. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8 squares. It's not going to be an easy one to do, but I reckon if I made every 5 squares equal to 100, that'd be 80, 100, 120, 140, 160, 180, 200. Well, that's pretty good actually. So that's what I'll start with. Hang on, that's pressure, isn't it? So it's 80, 100, 120, 140, 160, 180, 200. And I'm just going to make a little note. Remember to label my axes. Name, pressure, symbol P, unit, pascals. Well, actually, it's kilopascals. I need to remember that because I'm probably going to have to measure the gradient at some point. Now, what we do then is we want to find the absolute temperature. And again, the lowest value is about 280. My highest value is about 630. So 630 minus 280 gives me 350. So if I went 100, 200, 300, 350 wouldn't quite fit. So I'm going to need to be a little bit more conservative about this. So let's have a quick think. What can I do here? Well, if I'm saying that that's going to be, if I said that was 250, that'll be 300, 350, 400, 450, 500, 550, not enough room. So I'm going to have to go down to scales of 1. It's not going to be the best use, but never mind. So maybe this would start at about 200, 300, 400, 500, 600. Yeah, it's not brilliant, but it'll do. So it's the best we can do. Arrows on the axes, and this is going to be absolute temperature. And that's going to be capital T, name, symbol, unit, Kelvin, and then you plot it. So just going to take a little bit of care when you're plotting it. So we're plotting our results. You fold that in half so I can see it more clearly on camera. So the first one's at 90 and 283. So 90 is about there, 283 is about there. So I'll just join the 2 up like that. That'll do nicely. The next one's at 100, and that's at 314. So it's 300, 310, 314 is about halfway. Now I'm using quite a blunt pencil, by the way, so that you can see my marks, but you should use a sharp pencil when it comes to real exams. Right, 110 is 346. So that's 300, that's 110 there. 300, 10, 20, 30, 40, 46 is about halfway. The next one is 130, so I'm going to skip a few now. 130 would be 408. 400, well, 410 is there, so it's just before 410. 140 is going to be 440. So that's 140, so that's 100, that's 400, 10, 20, 30, 40. Next one is 170. So I'm taking quite a big jump now. 170 is 534. So there's 500. So 10, 20, 30. 34 is about halfway there. That'll do nicely. And then 200 is 629. So there's 600. 610, 20, 29 is just before 30. So I'll put my cross just before the 3 there. And you draw a nice line of best fit, okay? Should go through most of the points with equal numbers of points above and below the line. So you just need to be a little bit careful. I think most of these are actually falling on the line quite perfectly anyway. But there is my line of best fit. In fact, it goes through all my points quite happily. The next thing to do, it tells me, I've done that. I've drawn my line of best fit. Explain whether or not this proves a constant volume gas law. Now, when you want to prove the constant volume gas law, you know that the pressure is proportional to absolute temperature. So, P over T must always be a constant. So, what we need to do is we need to read it from the graph. And we're gonna take a little shortcut here. You'll see in a minute. If you box clever and read ahead, you can see that you can measure the gradient. You're going to have to be asked to measure the gradient of the graph. So I can make my life a lot easier, because to prove that two things are proportional, you have to divide them and always get the same number. So, for example, if I pick 3 convenient points, when you're doing a gradient, you have to pick 2 anyway. So you might as well use almost exactly the same reading. So we've got 1 there. I'm going to call that 1. We've got 1 about here. And then we'll pick one that's a bit further down, that's down here somewhere. That'll do. Okay. So we've got 1, 2, and 3. And I'm going to draw my working lines on here. My working lines show what they do is they show that you know how to do this. Okay. So this is 680. Okay. This one here is 200, 210, 20, 40. So that's 200, 214. Okay. So it's pressure over volume, pressure over temperature is a constant. So we start off with pressure is 214 divided by 680. Okay, calculate it. Comes out to be 0.31. So that's 1, 2, and 3. So we pick number 2. Again, we show construction lines. So that's 490. And that is 156. Okay. So it's 156 over 490. Comes out to be 0.32. And then the third one, well, that's going to be 270. Sorry, yeah, 270. And corresponding to 86. So it's 86 over 270. Comes out to be 0.32. So they're very similar. So that proves the pressure is proportional to the temperature, because we divide the pressure by the temperature every time, you get the pretty much the same number. You get a constant. Now, the next part of this asks you to calculate a gradient. And this is where boxing clever comes in really handy. Okay, if you're very clever, you realize you've already picked your 2 points. So all you've then got to do is draw your triangle based on those points. And you've already got your readings of y1 and y2. You don't actually have to further annotate your graph. You've just saved yourself a lot of bother. Okay, I'm just going to put my arrows on to show that this is the triangle I have used to calculate my gradient. Okay, so then I just say that my gradient is y1 minus y2 over x1 minus x2. So y1 is 214, y2 is 86. So it's 214 minus 86 divided by, let's see, we got 680 minus 270. Okay, so 214 minus 86 gives us 128 over 860 minus 270. It's 590. Which we've already got the value. We've already got the value, really, but we're really just doing this for form's sake, because it was in the previous question. Yeah, 0.22-ish. I'm just going to double check that. Okay, double check. I got that right? 860? Did I say 860? No, 680. That's what was wrong. That's where checking comes in handy, you see. You check it, realize you made a mistake, you correct it. 410. So whenever you make a mistake, you just put a neat cross through it. You don't scribble, you don't try and write over it. You see how that's not very clear? That's very clear. So .31, yeah, that's more like it. 0.31. So the gradient is 0.31. Now, I've got to be careful. It's y over x, so it's kilopascals per Kelvin. So you've got to be very careful. Remember, it's kilopascals per Kelvin. Right. Now, I'm going to do a little thing here because I'm reading ahead and I realize I'm going to have to use my value for gradient. So what I have to do is be a little bit sensible. I'm saying, well, okay, if that's 0.31 kilopascals per Kelvin, I know that that is 310 pascals per Kelvin. Okay. The reason being is I've now got that down to something a bit closer to sort of units without a prefix, because I know I'm going to have to calculate my gradient. So I've got to get rid of all those little prefixes anyway. So this just saves me a lot of bother. So the equation linking volume and pressure on a gas is given by a particular formula. Here it is. Hello, we've got P on the Y, T on the X. It says use your answer to part C, part 4 to calculate the number of moles of gas in the cylinder. So what we're doing is we're using PV is equal to nRT. Well, what we're actually doing is using Y equals MX plus C. So we're expecting a straight line through the origin, which is what we got, which proves they're proportional. This bit is the golden bit. That is your gradient, because that's on your pressures on your y-axis, absolute temperature on the x-axis. So your gradient is nR over V. So the gradient is equal to nR over V. Okay, you can look up most of these values now. So, want to work out N. N is the gradient multiplied by V divided by the molar gas constant. So N equals the gradient, 310, multiplied by the molar gas constant, divided by the volume. What does it tell you the volume is? There it is, 10 to the minus 3, 1.0 times 10 to the minus 3. And you can calculate it. That doesn't look right. Let's try again. I know what I've done wrong. Made a mistake. That's what I've done wrong. That makes sense now. Let's try that out. .03 moles, 0.337. 0.037 moles. Okay. Predict what the temperature would be for a pressure of 250 kilopascals in this experiment. Well, we're assuming that it's still got constant volume, so we can actually use the idea that P1 over T1 equals P2 over T2. Now I'm going to be careful here, double check. What I want, that's my P2. So P1 over T1. I want to find out what T2 is. So T2 is equal to P2 times T1 over P1. Now that's the same thing as saying, and you'll see why I'm doing this in a second. The reason why is in a previous question, we've got a value for P over T. And it's a constant, so 0.32 or 0.31. Okay, so that then makes life a lot easier. Well, I say, well, if that's the case, I could say it's 250. I'm going to ignore the kilo bit, divided by 0.31, which is my gradient. .806 Kelvin. Job's a good one. There are lots of different methods. They might get slightly different values, but it's technique, not answer, really. That's the important bit here. Right, so we're on to the next one. The next one is, we've got a balloon. So you always get this in your Unit 3 exams. In your Unit 3 exam, you get some kind of container of gas. Now we've got 1 cubic meter of helium. That's rather a big balloon. Is pumped into the balloon, adds a temperature of 250 degrees Kelvin, and assume atmospheric pressure, 100 kilopascals. Show there are 48 moles of helium in the balloon. So what we're using is PV equals nRT. I want to find out N, PV over RT. So the pressure is 100,000 multiplied by volume, which is 1, divided by the molar gas constant, and also divided by the temperature, which is 250 Kelvin. I don't even have to convert that. And it comes out to be, well, it's about 48.1. We'll call it 48. Mole. There we are. Job done. That's easy. Helium's got a molar mass of 4 grams per mole. Well, calculate the mass of helium balloon. Well, that's a no-brainer. We know that that would be the mass of the helium in the balloon would be the number of moles multiplied by the molar mass. So that's 48 multiplied by 4 grams. Now, careful, it's 4 grams, 0.004 kilograms. 0.192 kilograms. Just going to pause for a second while I quickly sharpen my pencil. It's gone flat, it's gone blunt. Right, so I've just swapped over to my pen. Where it's not clear, put a line through and write the answer in as clearly as possible. There we are. Don't forget the units, it's important. Then says calculate the number of helium atoms in the balloon. Well, to get the number of helium atoms, you want Avogadro's number multiplied by the number of moles. So it's 48 multiplied by 6.02 times 10 to the power of 23. Okay. And so that comes out to be 2.89 times 10 to the power of 25 atoms. And we could say atoms because helium's monatomic. You don't need to know that. This number is Avogadro's number. It is on the formula sheet, on the data sheet, inside the front cover of your exam papers. Right, next one. Calculate the kinetic energy, the average kinetic energy of one atom of helium at 250 Kelvin. So to get the kinetic energy, it's 3 over 2 times the Boltzmann constant times the absolute temperature. So 3 over 2 is 1.5. Boltzmann constant is 1.38 times 10 to the minus 23. Okay. Multiply it also by the absolute temperature, 250. And that gives you the average kinetic energy of one atom of helium, which comes out to be 5.18 times 10 to the minus 21 joules. Okay, so that then is the kinetic energy of one atom according to this formula. A lot of people get really confused because they start getting worried because we associate the speed, the mean square speed of a particle with the temperature. So they think, well, how come the mass doesn't make a difference? Well, don't forget there are two things that affect energy. There's mass and velocity. So the velocity of helium particles is much higher. Right. Hence calculate. Now, hence means using the previous answer, not other methods. Calculate total internal energy of the helium in the balloon. So to get total internal energy,
period 4 ends.
Sorry about that. It would be the energy of one atom multiplied by the number of atoms. So the number of atoms in our previous answer was 2.89 times 10 to the power 25. So that's the answer we give. Okay. So that's the energy of one atom. Sorry. That's the energy of one atom, and that's the number of atoms. So that gives you the total energy. And we're expecting a sort of a macroscopic number, aren't we? So it would come out to be about 1.50 times 10 to the power of 5 joules, according to my calculations. Okay, and that would be the energy of 129 grams of any particular gas. Now, then we're going into part C. And when the balloon reaches its maximum altitude, the temperature is minus 13 degrees Celsius. Well, it's gas laws. You know, 273 minus 13, because it's minus 13 is 260. You know you're going to have to do that at some point anyway. So you want to work out the new volume of the balloon. So we've got a particular volume. We knew it was 1 cubic meter, but now we've got a new volume. There are a couple of different ways of doing this. One is to use the equation of state, the PV is equal to nRT. We can do that. That's absolutely no problem whatsoever. Or you could do it by using ratios. We might as well use PV is equal to nRT. Okay, so now he wants to know the new volume. It's V equals nRT over P. So it's the same amount of gas, 48 moles, multiplied by molar gas constant, which is 8.31, multiplied by the absolute temperature, it's 260. I told you we'd need it, divided by the pressure, which is 8 times 10 to the power of 4. And we end up with, well, we're expecting a slightly expanded balloon here. And lo and behold, it comes out to be 1.30 meters cubed. Okay, there's your answer. Now, what is the root mean square speed of helium atoms at this new altitude? Well, basically, we know that it's pretty easy to do. We know that we're using volumes and pressure. We know that PV is equal to 1/3 nm times the mean square speed, and that's the value we want. So the mean square speed, which is the speed squared and then added together and then divided by the number of particles. So we end up with 3 PV over nm. So it's 3 times the new pressure, which is 8 times 10 to the power of 4, times by the volume, which we now worked out to be 1.30. Sorry about that. Hundreds of people will want to speak to me all at the same time. So divide it by the number of atoms. Well, how am I going to find the number of atoms? Well, it's a previous answer to a question, isn't it? So let's have a look. Have I got a previous number? Have I got a number of atoms here somewhere? Here we are, 2.89 times 10 to the power of 25. So that's easy. So that's 2.89 times 10 to the power of 25, multiplied by the mass of each atom. Ooh. Well, there must be an easier way to do it than that. Well, actually, that is the total mass of the gas. That's the number of atoms, that's the mass of each atom. So the total mass of the gas I already know, because again, that's in my answer here, 0.192 kilograms. So that comes out to be 0.192, which by my reckoning comes out to be about 1.62 times 10 to the power of 6 meters squared per second squared, because that's the mean square speed. So to get the square speed, to get the root mean square speed, I have to square root it. That's because it says root mean square speed. So I have to square root it. If I have to square root it, that's easy to do. Square root of that number comes out to be 1,300 meters per second. There's your answer. Okay. Right, moving on. At higher altitudes, the pressure will continue to decrease, but the temperature will increase slightly. Explain why the weather balloon is unlikely to be able to go much higher. Well, if the pressure decreases and the temperature increases, the volume will continue. The volume will continue to increase until the balloon bursts. Since pressure decreases, and temperature increases. Okay, you can even say if PV equals nRT, then the volume is going to be nR over T, well, multiplied by T over P. So T goes up, P goes down, V has to go up and up some more. Okay, so the balloon will burst. Okay, and that's actually what happens to weather balloons. That's how when you see that film footage of people sending helium balloons up to the edge of space, and then they suddenly fall back down. That's what actually happens. The balloon bursts. Right, list the 5 assumptions. This is the bit that really gets people. 5 assumptions. So the first one is particles move in random directions. Whoops, bad my handwriting. Okay, they move around at random. They won't be moving in different directions at a range of speeds. Okay, they're not all moving. Not all the height of the helium atoms were moving at 1,300 meters per second. There's some moving faster, some moving a bit more slowly. Well, it's a mean. Okay, we know also that there are many particles. We know the size of particles is negligible compared to the volume of gas. We know there's no intermolecular forces. Oh dear. There's no intermolecular forces. And we can also assume all collisions are elastic. Okay, because we know the particles move in random directions at a range of speeds. We know that because a vessel of gas doesn't start shooting across a room or anything like that. So they're all moving in opposite directions, such that their average velocity is 0 meters per second. There are many particles. Well, you don't see a balloon sort of having little bits bulging out or anything like that. The size of the particle is negligible compared to the volume of gas. Well, that's why you can compress it. No intermolecular forces. Well, that's true. Otherwise, the gases would naturally become solids without any change in temperature. And all collisions are elastic. Well, that makes sense because otherwise the speed of the particles would decrease, and therefore the gas would lose internal energy, so it would cool down. Everything in the universe would be at 0 degrees Kelvin by now. Okay, so that is the big 18 marker. So you've got your 5 assumptions. Now your next one is thermal expansion, and again, it's all just practice. So this is not the best question I've ever written. There are a few mistakes on it. Must have been getting tired as I was writing this paper. So we've got the height of the container at 0 degrees Celsius is 0.2 meters. Material of the probe is iron. The linear coefficient of expansion of iron is supposed to be that number. That's actually not the correct number for it, but it doesn't matter. We can still do the practice with it. So the height of the container at 600 degrees Celsius is going to be the original height plus, well, for thermal coefficient, we know it's going to be the original length, or in this case height, multiplied by 1.17 times 10 to the minus 6, multiplied by the change in temperature. Well, at 600 degrees Celsius, it starts off at 0, so that would be 600, which gives me 0.20014 meters. Okay, that's the first one. Second one, calculate the height of the container at minus 150. We do exactly the same, only this time it's cooled down. So we've got to subtract. So that then comes out to be 0.19986 meters. Okay. So discovering what might happen to the container if it was transferred from its coldest extreme to the hottest extreme very suddenly. Well, what's going to happen with anything is it will expand rapidly. Okay, but not evenly. So the parts on the iron on the inside of the vessel is not going to expand as quickly as the rest of it, because it won't be warming up as quickly, and that means that stresses build up. stresses build up, and because the stresses then build up, it could shatter. It could buckle. It could just break. I don't mind. It's 1 mark for explanation, 1 mark for the end result. Next one is you have to place across to all the materials which expand more than iron at high temperatures, and in fact it's all of them. It's suggested that the container could be made out of chromium. Explain why chromium would be better than the choice of materials of higher and lower values. So if we look at chromium, it's got somewhere between 6 and 7. So higher value, okay, the material would expand more. Okay, so it could expand and contract more, so it could break. The reason why you wouldn't use the lower material, the only material there that is lower is the glass. So if the glass is lower, well, glass is brittle. And so that will definitely shatter if you try and heat stuff and cool it down too quickly. So there's a little bit of a trick question there. Right, question 4. Use the first law of thermodynamics to explain why. You need to eat less in hot climates. Well, the first law of thermodynamics says the change in energy is equal to the heat energy supplied plus the work done. Okay. Now, if you think about it, you need less energy to keep your body warm. Okay. You still do the same amount of work. So less energy is used. Okay. You could, applying it to the first law of thermodynamics, that is your food. That's your food intake. That's your food energy. That's the energy you use to keep warm. And this one is the energy you'd use to do work, to do your day-to-day sort of moving about and talking and thinking. Okay. If that's reduced, and that's the same, then that's reduced. And if that's reduced, then you need less food. Simple as that. The gas coming out of a fire extinguisher is cold. Well, again, change in internal energy, which is related to temperature, is equal to Q plus W. So when the gas comes out of a fire extinguisher, it expands rapidly. So it is mainly an adiabatic change. Okay, so it's mainly an adiabatic change. Does work on the atmosphere. In other words, by the gas. And therefore the internal energy decreases. Okay. So that's equal to 0. We know that will be negative. And so this would be negative. Change in internal energy would be negative, so the gas would cool down. Pretty simple, isn't it? Very simple when you think about it. Right, on to multiple gas. Multiple gas times. So we're starting off with this question number 7. No, we're starting off with this one, question number 5. So the temperature of a body at 100 degrees Kelvin is increased by delta theta as measured on the Kelvin scale. How is this temperature change expressed on the Celsius scale? It's exactly the same increments. Trick question. Loads of people start adding 273 or subtracting 273. It's not. It's the temperature change. Read the question carefully. Number 6 was the approximate number of atoms in 2 cubic meters of an ideal gas at a temperature of 27 degrees Celsius. So that would be 300 Kelvin. You always get questions about 300 Kelvin. Number of atoms, so that's going to be the equation of state, but using big N instead of little n. So we use PV equals NKT. Want to work out what N is? So it's PV over NK. So we use pressure is 10 to the power 5. Volume is 2 cubic meters. Oh, not NK, it's KT, isn't it? And T is 300. And K is 1.38 times 10 to the power of minus 23. And we end up with D, according to my calculations. So number 7, for a fixed volume of an ideal gas raised from 300 to 330 Kelvin, so it's fixed volume. The mean energy of the particles of the gas increases by 10%. That's correct. The root mean square velocity of the particles of the gas increases by 10%. That's not correct, because you know that the temperature is proportional to the kinetic energy. So that's the mean square speed, and that's the root mean square speed. So that would not be correct. Okay. So the number of collisions of the walls in the container increases by 10%. Well, that's not quite right, is it? If it's a fixed volume of gas, we know the pressure will increase by 10%, but the pressure isn't just dependent on the number of collisions per second. It's also to do with the kinetic energy, with the momentum of the particles. Therefore, 3 is not necessarily correct. So only 1 is the right answer. There can be only 1. 5 molecules moving with the speeds and directions shown. Well, we want to calculate the root mean square speed. So that's 300 squared plus 100 squared plus 300 squared plus 300 squared plus 500 squared, all divided by 5. And I reckon that would then give you a number, but what we've got to do, remember, it's root mean square speed. So we've got to take all of that and square root it. And the answer comes out to be C, 325 meters per second. Okay. Number 9, what's the work done in the atmosphere increasing the pressure of an ideal gas from 100 kilopascals from 1 meter cubed to 1.5 meter cubed in the isobaric process? So we're keeping the pressure constant. So the work done is P times the change in volume. Okay, something you need to know. So that would be pressure is 10 to the power of 5, because it's kilopascals. The change in volume is 0.5, because it goes from 1 to 0.5. Okay, so the work done is 50,000 joules. Easy. And last but not least, number 10. Which of the following does not change during an isochoric change? Is it temperature, volume, internal energy, pressure? Well, isochoric means constant volume. So the thing that does not change is volume. And it's as easy as that. What I'd like you to do, if you haven't already done so, download the paper that I attached to the previous lesson, and I'll need you to use this walkthrough to go through that paper. I want you to have a go at answering these questions. It's really important. If you don't learn how to answer these questions, I'm going to say it. If you don't learn how to answer the questions, you've got very little chance of being able to pass the UFP exams. So please make sure that you have a look at the questions and make sure you practice and learn the techniques I'm showing you. I'll see you next lesson.